Microsoft Azure and Amazon Web Services are the two largest cloud platforms, commanding 50% of the global market, AWS at 30%, Azure at 20%. Azure ML and AWS SageMaker are their machine learning services for the entire ML lifecycle. Data preparation, training, deployment, and monitoring. Both platforms offer similar capabilities, but they differ fundamentally in how they're designed. Which one should you choose? We will compare Azure ML and SageMaker for a critical ML scenario, training models at scale using jobs. Firstly, let's use an analogy to understand why training jobs matter. Jupyter notebooks work for experimentation on a single device, but they don't scale to production. Training jobs let you deploy tasks across multiple cloud instances, running longer and processing more data. Think of it like this. A Jupyter notebook is developing a dinner recipe. A training job is hiring a catering team to cook it for 500 customers. Everyone needs the same ingredients, recipe, and tools. Now that we understand the importance of training jobs, let's look at how they're defined in Azure ML versus SageMaker. We'll break down the comparison into 4 key dimensions. Start with project setup and permission management, then move into storing and accessing data, and finally explore the compute resources and runtime environments that power model training jobs. If you would like to read the blog post that covers these concepts in more details along with the code snippets, please check out the link in the description. Let's start by understanding a typical ML workflow in a medium to large team of data scientists, data engineers, and ML engineers. Each member may specialize in a specific role and responsibility and be assigned to one or more projects. For example, a data engineer is tasked with extracting data from the source and storing it in a centralized location for data scientists to process. They don't need to spin up compute instances for running training jobs. In this case, they may have read and write access to the data storage location, but don't necessarily need access to create GPU instances for heavy workloads. Depending on data sensitivity and their role in an ML project, team members need different levels of access to the data and underlying cloud infrastructure. We're going to explore how the two cloud platforms structure their resources and services to balance the requirements of team collaboration and responsibility separation. Project management in Azure ML is workspace-centric. You start by creating a workspace under your Azure subscription ID and resource group for storing relevant resources and assets, shared across the project team for collaboration. Permissions to access and manage resources are granted at the user level based on their roles. This is called Role-Based Access Control, or RBAC. Generic roles in Azure include owner, contributor, and reader. ML specialized roles include Azure ML Data Scientist and Azure ML Compute Operator, which is responsible for creating and managing compute instances as they are generally the largest cost element in an ML project. The objective of setting up an Azure ML workspace is to create a contained environment for storing data, compute, models, and other resources, so that only users within the workspace are given relevant access to read or edit data assets, or use existing or create new compute instances based on their responsibilities. In this code snippet, we connect to the Azure ML workspace through ML Client by passing the workspace's subscription ID, resource group, and the default credential. When developers run code during an interactive development session, the workspace connection is authenticated through the developer's personal credentials. They would be able to create a training job. To detach personal account credentials in the production environment, it's recommended to use a service principal account to authenticate for automated pipelines or scheduled jobs. Roles and permissions in SageMaker are designed based on a completely different principle, primarily using roles in AWS Identity and Access Management Service allows creating user-level access similar to Azure. AWS recommends granting permissions at the job level throughout the ML lifecycle. In this way, your personal AWS permissions are irrelevant at runtime, and SageMaker assumes a role, called the SageMaker execution role, to access relevant AWS services. This includes S3 buckets, SageMaker training pipelines, and compute instances for executing the job. Here's a quick example of setting up an estimator with the SageMaker execution role for running a training job. This means we can set up enough granularity to grant role permissions to run only training jobs in the development environment, but not touch the production environment. For example, if the role is given access to an S3 bucket that holds test data and is blocked from the one that holds production data, then the training job that assumes this role won't have the chance to overwrite production data by accident. Permission management in AWS is a sophisticated domain by itself, and we won't dive too deep into every detail here. Now let's explore how Azure and AWS handle data storage for training jobs. You may have the question, can I store the data in the working directory? That's been my question for a long time, and I believe the answer is still yes if you're experimenting using a simple script or notebook in an interactive development environment. But data storage location is important to consider for creating ML jobs. Since code runs in a cloud-managed environment or a Docker container separate from your local directory, any locally stored data cannot be accessed when executing pipelines and jobs. This requires centralized, managed data storage services. In Azure, this is handled through a storage account within the workspace that supports data stores and data assets. Data stores contain connection information, while data assets are version snapshots of data used for training or inference. Since data stores securely keep data connection information and automatically handle credentials and identity behind the scenes, they decouple data location and access permission from the code. This means the code remains unchanged even if the underlying data connection changes. Data stores can be accessed through their unique URI. Here's an example of creating an input object with the type URI_file by passing the data store path. Data asset is another option to access data in an ML job, especially when it's beneficial to keep track of multiple data versions, so data scientists can identify the correct data snapshots being used for model building or experimentation. Here's an example of creating an input object with asset types.uri_file type by passing the data asset path and using the mode ro_mount for read-only access. AWS, on the other hand, relies heavily on S3 buckets as centralized storage locations that enable secure, durable, cross-region access across different accounts, and users can access data through its unique URI path. SageMaker training jobs, inference endpoints, and pipelines can process input data from S3 buckets and write output data back to them. Unlike Azure ML's workspace-centric data store approach, AWS S3 is a standalone data storage service that offers more flexibility for permission management at the individual folder level, but at the same time requires explicitly granting the SageMaker execution role access to the S3 bucket. In this code snippet, we use estimator.fit passing the training data S3 URI directly. The model is trained and outputs are stored at the specified S3 bucket location. Now that we've explored how Azure and AWS take fundamentally different approaches to machine learning project management and data storage, let's examine the compute resources that power model training jobs. Compute is the virtual machine where your model and code run. Along with network and storage, it's one of the fundamental building blocks of cloud computing. Compute resources typically represent the largest cost component of an ML project, as training models, especially large AI models, requires long training times and often specialized compute instances, like GPU instances, with higher costs. This is why Azure ML designs a dedicated Azure ML compute operator role for managing compute resources. Azure and AWS offer various instance types that differ in the number of CPUs and GPUs, memory, disk space, and type, each designed for specific purposes. Both platforms use a pay-as-you-go pricing model, charging only for active compute time. Azure Virtual Machine series are named in alphabetic order. For instance, the D family VMs are designed for general-purpose workloads and meet the requirements for most development and production environments. AWS compute instances are also grouped into families based on their purpose. For instance, the M5 family contains general-purpose instances for SageMaker ML development. Please note that pricing structures vary by region and plan, so it's recommended to check their official websites. Computes are persistent resources in the Azure ML workspace, typically created once by the Azure ML compute operator and reused by the data science team. Since compute resources are cost-intensive, this structure allows them to be centrally managed by a role with cloud infrastructure expertise, while data scientists and engineers can focus on development work. Azure offers a spectrum of compute target options designated for ML development and deployment, depending on the scale of the workload. A compute instance is a single-node machine suitable for interactive development and testing in the Jupyter Notebook environment. A compute cluster is another type of compute target that spins up multi-node cluster machines, can scale for parallel processing, and supports autoscaling by configuring minimum and maximum instances. Additionally, there are serverless compute, Kubernetes clusters, and containers that are fit for different purposes. To create an Azure ML managed compute target, we create an AML compute object using this code. Type: use AML compute for compute cluster, alternatively, use compute instance for single-node interactive development. Name: specify the compute target name. Size: specify the instance size. Min instances and max instances: set the range of instances allowed to run simultaneously, this is optional. Idle time before scale down: automatically shut down the compute cluster when idle to avoid incurring unnecessary costs, also optional. Once the compute resource is created, anyone in the shared workspace can use it by simply referencing its name in an ML job, making it easily accessible for team collaboration. Compute resources are managed by a standalone AWS service called EC2, Elastic Compute Cloud. When using these compute resources in SageMaker, developers must explicitly configure the instance type for each job. Compute instances are created on demand and terminated when the job finishes. This approach gives developers more flexibility over compute selection based on task, but requires more infrastructure knowledge to select and manage the appropriate compute resource. As shown in this code snippet, AWS SageMaker specifies the compute instance and the number of instances running simultaneously as job parameters. A compute instance is created during job execution and charged based on the job runtime. SageMaker jobs spin up on-demand instances by default. They're charged by the second and provide guaranteed capacity for running time-sensitive jobs. For jobs that can tolerate interruptions and higher latency, spot instances are a more cost-saving option that utilizes unused compute instances. The downside is the additional waiting period when there are no available spot instances. We use this code snippet to implement a spot instance option for a training job. To use spot instances, set this parameter as true. Max wait refers to the maximum amount of time you're willing to wait for available spot instances to become available, and importantly, you are not charged for this waiting time. Max run specifies the maximum amount of training time allowed for the job to complete. Checkpoint S3 URI is the S3 bucket URI path where model checkpoints are saved, which allows training to safely restart from the last checkpoint after the waiting period. Lastly, let's compare how Azure ML and AWS SageMaker approach runtime environment setup. Environment defines where the code or job is run, including software, operating system, program packages, Docker images, and environment variables. While compute is responsible for the underlying infrastructure and hardware selections, environment setup is crucial in ensuring consistent and reproducible behaviors across development and production environments. This mitigates package conflicts and dependency issues when executing the same code in different runtime setups by different developers. Azure ML and SageMaker both support using their curated environments and setting up custom environments. Similar to data and compute, environment is considered a type of resource and asset in the Azure ML workspace. Azure ML offers a comprehensive list of curated environments for popular Python frameworks like PyTorch, TensorFlow, and scikit-learn, designed for CPU or GPU targets. This code snippet helps retrieve the list of all curated environments in Azure ML. They generally follow a naming convention that includes the framework name, version, operating system, Python version, and compute target, CPU or GPU. To run a training job in a curated environment, we create an environment object by referencing its name and version, then pass it as a job parameter. Azure ML also supports custom environments from a Docker image by providing the Docker image URI. SageMaker's environment configuration is tightly coupled with job definitions, offering 3 levels of customization to establish the OS, frameworks, and packages required for job execution. These are built-in algorithm, bring your own script, also called script mode, and bring your own container, or BYOC. They range from the most simple but rigid option to the most complex but customizable option. Built-in algorithms are the option with the least amount of effort for developers to train and deploy machine learning models at scale in AWS SageMaker. Azure currently does not offer an equivalent built-in algorithm approach using Python SDK. Bring Your Own Script allows developers to leverage SageMaker's pre-built containers for popular Python frameworks like scikit-learn, PyTorch, and TensorFlow, customizing the training job through your own script without the need to manage the job execution environment. Bring Your Own Container allows developers to bring a custom environment using a Docker image, build and push it to Elastic Container Registry, or ECR, and reference the image URI when creating the estimator. Let's recap. Based on the comparisons of 4 dimensions: project permission management, data storage, compute, and environment, we can see the Azure and AWS adopt different design principles to structure their machine learning ecosystems. Azure ML follows a modular architecture where data, compute, and environment are treated as independent resources and assets within the Azure ML workspace. Since they can be configured and managed separately, this approach is more beginner-friendly, especially for users without extensive cloud computing or permission management knowledge. For instance, a data scientist can create a training job by attaching an existing compute in the workspace without needing infrastructural expertise to manage compute instances. On the other hand, AWS SageMaker has a steeper learning curve, as multiple services are tightly coupled and orchestrated together as a holistic system for ML job execution. However, this job-centric approach offers clear separation between model training and model deployment environments, as well as the ability for distributed training at scale. By giving developers more infrastructure control, SageMaker is well suited for large-scale data science and AI teams with high MLOps maturity and the need for CI/CD pipelines. Thanks for reaching the end. Please comment down below which topic you'd like to learn more about in our next video. Like and subscribe for more videos like this.